This video is going to cover the wave calculation practice worksheet. For an in-depth description of how these wave equations work and what the variables mean, check out the example problems that were posted. Those are going to be a little bit more explaining the meaning behind all of this. This is just going to go through the process of solving each problem. I expect that you have a little bit of familiarity with the concepts before going into this worksheet. So again, if you want a more in-depth look at these different equations and how they work, go watch the wave calculation examples video and then move on to the practice worksheet. So the first thing I want to review is that there are some different variables that we'll be dealing with. Lambda, which looks like an upside down y, that is the wavelength, and it is measured in meters. So anytime that you're using the equations, you need to have lambda in meters. It will come out of the equation in meters. That letter, the letter that looks like a V, is called nu, and that represents the frequency, which is measured in hertz. And then E is energy, and that is measured in joules. The only other two things that you'll see in these equations are C, which is the speed of light, 3.00 times 10 to the 8th, or 300 million meters per second. And H, which is Planck's constant, that's 6.626 times 10 to the negative 34th joules per hertz. So question number one here is what is the wavelength of a wave having a frequency of 3.76 times 10 to the 14 hertz? In this case, we're relating wavelength and frequency, so you have to go up in your equations and try and find the one that has wavelength and frequency. Again, those are lambda and nu as the variables. So if you look through those different equations, you should see that C equals lambda nu is the one that is most fitting this problem. And then we just need to plug in our numbers. So C is always 3 times 10 to the 8th, so 3.00 E8. Lambda, the wavelength, is what we're looking for in this problem, and nu, the frequency, is 3.76 times 10 to the 14th hertz. To solve for lambda, we're going to divide both sides by 3.76 times 10 to the 14th, and so what we end up with is 3.00 E8 divided by 3.76 times 10 to the 14th is going to give us our lambda. If you put that into your calculator and you round your answer to three significant figures, you should get 7.98 times 10 to the negative 7th. And then, since it's lambda, that is wavelength, it's going to come out in units of meters. For problem number 2, it says, what is the frequency of a 6.9 times 10 to the negative 13th meter wave? So this one is giving us frequency. Now, it doesn't tell us exactly what the 6.9 times 10 to the negative 13th is, but we have that it's in meters. So that lets us know that we're talking about a wavelength here. So again, we've got this equation, which is relating frequency and wavelength. This time we're given the wavelength, and we're supposed to find the frequency. So we're going to use that same equation again, C equals lambda nu. We're going to plug in our numbers, 3.00 E8 equals lambda, that's our wavelength, is 6.9 E negative 13. And then nu is our unknown in this one. To solve for nu, we're going to divide both sides by 6.9 times 10 to the 13th. So we end up with 3.00 E8 over 6.9 times 10 to the negative 13th equals nu. And when we go through and we do that calculation, we find that nu equals 4.3 times 10 to the 20th hertz. All right, hertz because frequency is always measured in units of hertz. Hertz means cycles per second, so 4.3 times 10 to the 20th cycles per second, which is a lot of cycles per second. Something to notice about this is that the frequency of these electromagnetic waves can be really, really high. One other thing I want to mention about this is the answer was rounded to 2 significant figures. The reason that this was rounded to 2 significant figures is because 6.9 times 10 to the negative 13th was originally 2 significant figures, and we have to keep the lowest number of sig figs that were given to us in the problem. Continuing on, problem number 3. So problem number 3 says, what is the wavelength of a 2.99 hertz wave? Again, this doesn't say exactly what variables we're looking at, but it says wavelength for one, and then if you're savvy about the units, you know that hertz measures frequency. So this is another one where we have wavelength and frequency. We're going to use that same equation again. C equals lambda times nu. This should be getting pretty familiar at this point, so 3.00 times 10 to the 8th equals, our unknown is the wavelength this time, so lambda is our variable, and then nu, the frequency in this case, is just 2.99. To solve for lambda, we're going to divide both sides by 2.99, and you get 3.00 times 10 to the 8th divided by 2.99 equals lambda. Right. Putting that into the calculator, we get 1.00 times 10 to the 8th and then the unit on this, because it is wavelength, is meters. Problem number 4. This is another one with frequency, and then we're given units of millimeters this time. This is a little bit tricky because millimeters is not the correct units to be plugged into these equations. If you're going to be plugging something in, it should be in meters. So that means we're going to do a little conversion before we put the numbers in. So it starts off at 7.43 times 10 to the negative 5th millimeters. I think it's going to be easier for us to do this conversion if we just write that out in standard notation. So this is 0.0000743 millimeters, just converting from scientific notation to standard notation. Now, if we're going from millimeters to meters, we're going to have to bump the decimal place over 3 spots. So we're moving 3 spots over to the left, going from millimeters to meters. So 1, 2, 3 spots over. And so what we end up with is 0.000000743 meters. Alternatively, if you are interested in keeping this in scientific notation and you know that you're moving the decimal spot over 3 places, it's going to be 7.43 times 10 to the negative 8th. That might make more sense to people who are really good at math. I'm going to leave it this way. So that is going to be our wavelength in this case. So we're going to now plug it into the equations. We've got C equals lambda times nu, which means we've got 3e8, or let's write it out, 3.00 to keep our sig figs there. 3.00 times 10 to the 8th. All right, equals that lambda, that big long 0.000000743 times nu. And so then what we end up with here is that we divide both sides by 0.0000743, and we get that nu is equal to 4.04 times 10 to the 15th hertz. Three significant figures here. The unit's hertz because it's frequency. All right, one last example here that also deals with frequency and wavelength. This time it's a little bit of an easier conversion because lambda is just going to be 26 meters, converting from centimeters to meters. So again, that's going to be the first step, is we're going to say lambda, converting it here, equals 26 meters. So that is in the right units now. And then we know C equals lambda times nu, 3.00E8 equals 26 times nu. Divide both sides by 26, so 3.00E8 divided by 26 equals nu, which equals 1.2 times 10 to the 7th hertz. The problems on the back have to do with energy, a lot of them, so we're going to have to use some of the other equations. Number 6 says, what is the energy of a 7.66 times 10 to the 14th hertz wave? So in this case, we are asking for the energy, and it's given us hertz, so that's the frequency. We need to find the equation that relates energy and frequency to one another. If you look back on the front, you can see the equation that has energy and frequency is E equals H nu. So that's what we're going to be using here. The energy is what we're trying to find. So this is going to equal here then 6.626 times 10 to the negative 34th. That is Planck's constant, that's always the same, times our frequency here, which is 7.66 times 10 to the 14th. If you just multiply those by each other, you should get 5.0 times 10 to the negative 19th, 5.08 times 10 to the negative 19th joules. This has 3 sig figs because 7.66 times 10 to the 14th had 3 sig figs. Problem number 7 is next. 7 says, what is the frequency? So again, we're talking about frequency and energy, right? What is the frequency of a wave carrying 8.35 times 10 to the negative 18th joules of energy? So we're going to write out the same equation. Energy equals H nu. So we've got 8.35 times 10 to the negative 18th equals Planck's constant 6.626 times 10 to the negative 34th times nu. All right, to solve for nu then, we're going to say 8.35 times 10 to the negative 18th, divided by 6.626 e negative 34 equals nu. And if you calculate that, then what you end up with is 1.26 times 10 to the 16th hertz. On to problem 8. 8 says, what is the wavelength of a 7.65 times 10 to the negative 19th joule wave? Convert your final answer to nanometers. So this problem is tricky for a couple of reasons. One, it relates wavelength and joules, which is energy, which is one of the more complicated equations that we have to deal with. It relates to E equals hc over lambda, right? Because that is the equation that has wavelength and frequency in it. And then we have to rearrange that equation to try and make it make sense to solve for wavelength. It's kind of hard to solve for things if we're plugging in numbers and the variable is in the denominator. So what we're going to do is we're going to multiply both sides by lambda and rearrange this equation a little bit. If you multiply both sides by lambda, you get E times lambda equals hc. And then we can go one step further, divide both sides by E, and then you get lambda equals hc over E. All right, so now we're ready to solve for lambda. We can just plug in the numbers. That is 6.626 times 10 to the negative 34th, Planck's constant, times the speed of light, which is c, that's 3.00 times 10 to the 8th. We divide that by 7.65. 7.65 times 10 to the negative 19th, which is our energy. And when you put that in, you get 2.60 times 10 to the negative 7th meters. Next, we need to convert it to nanometers. To get it to nanometers, we need to move the decimal place over 7 spots, and we'd be moving it 7 spots over to the right, which means that our exponent goes down by, I think I said 7 spots, I meant 9 spots. Our exponent is going to go up by 9, and so what we end up with is 2.60 times 10 squared, or just 260. So this is 260 nanometers. The last thing is we want this to have 2 significant figures, or 3 significant figures, because all of our numbers had 3, so 260 point nanometers is what we've got there. Number 9, what is the energy of a photon with 9,300 centimeter wavelength? Okay, so again, we've got energy, we've got wavelength, so we're going to be using E equals hc over lambda. Thankfully, on this one, we want energy, so it's already in the right form. So we just got to plug things in. H is 6.626 times 10 to the negative 34th. C is 3.00 times 10 to the 8th. And then lambda, we need to have it in meters, so we're going to move the decimal spot over 2 spots from centimeters, and it's just 93 meters, actually. We plug that into the calculator, and we get that energy equals 2.1 times 10 to the negative 27th joules. For this one, we had 2 significant figures because the original wavelength had 2 significant figures, so we have to round it to that level. For number 10, that's the last problem here, it says, what is the wavelength of a 1.528 times 10 to the negative 13th joule wave? This is relating wavelength and energy, and it is asking for wavelength. If you look back at our work above, you can see that we already solved this equation for wavelength, and you get lambda equals hc over E. We're going to take advantage of that equation again. Just plug in the numbers here. 6.626 times 10 to the negative 34th times 3.00 times 10 to the negative 8th, or positive 8th, divided by the energy, 1.528, times 10 to the negative 13th. And if you calculate that, you should get 1.30 times 10 to the negative 12th joules, or meters, because it's wavelength. I know that these problems are a little bit tricky, so if after watching this video you still have any questions about them, I encourage you to come in and ask.